Okay, I think it's time to start our Wyrzykowski and Leopold-Infeld colloquium. Welcome, everyone. Today we will have two speakers who will present achievements of this year's Nobel Prize winners. This will be Professor Jerzy Lewandowski, Chair of the Theory of Relativity and Gravitation at our Physics Department, Warsaw University, the President of Polish Society on Relativity and Fellow of International Society on General Relativity for his achievements in understanding the loop quantum gravity. And the second presenter will be Dr. In Polish habilitowany Łukasz Wyrzykowski, an astronomer who is from the Astronomical Observatory of Warsaw University. And in his research, he concentrates on observational astrophysics, studies of dark matter via microlensing and black holes with transient phenomena. And they will present, as I said, three winners of the Nobel Prize. Roger Penrose for showing that black hole is a robust prediction of general relativity, and Reinhard Grenzel and Andrea Goetz for discovery of supermassive compact object at the center of our galaxy. So the first speaker is Jerzy Lewandowski. So the screen is yours, please.
Good afternoon. My part is of this Nobel Prize will be Sir Roger Penrose. You can see him on the screen. Let me also express that it's a real pleasure for me to be presenting Roger's achievement. Unfortunately, he has so many achievements in general relativity, in physics, and even more. That it's really impossible to present all of them in detail. So maybe good that this Nobel Prize was just for his one or two, or a couple of papers. So it makes this task easier. So this is my first slide. I would like to begin my story on Roger somewhat in the middle, namely in Imperial College in London on the first week of July 1965. This is a few months after his seminal paper on singularity theorems has been published. I will base this introductory part on Kip Thorne's memories that are contained in fantastic book by Kip Thorne, Black Holes and Time Warps, Einstein's Outrageous Legacy. I recommend this book. If you start reading one page, you will spend next 2 days and nights reading all other 500 pages until you see the end. And this is a photo of Kip Thorne in elevator in Institute for Mathematics of Polish Academy of Science, which I took a few years ago when he was visiting us. It was a warm summer day in 1965. The world's leading general relativity researchers had gathered for the 4th International Conference on General Relativity. The speaker was very famous, so the lecture room was filled to overflowing as Isaac Kalatnikov rose to speak. He and Yevgeny Lifshitz in Moscow had proved, or at least so they thought, that when a real star with random internal deformations implodes, it cannot create a singularity at the center. This is Isaac Kalatnikov, and this is Yevgeny Lifshitz. And Yevgeny Lifshitz is a co-author of famous and very good a series of lecture course in theoretical physics together with Landau. And this is a photo of the volume field theory, Teoria Pola, because actually the result had been already contained in this book, as far as I understood. I didn't see that copy, but according to Kip Thorne, they already managed to include their result on singularities in this first version of this book. Kalatnikov spoke dragging a microphone with him, using the standard equation intensive methods known well to all the theoretical physicists. You should remember he was from Landau school, and he was one of leaders in this group of people working in Landau. He demonstrated that random perturbations must grow as a star implodes. This means, he asserted, that if the implosion is to form a singularity, it must be one with completely random deformations in its space-time curvature. He then described how he and Lifshitz had searched among all types of the singularities permitted by the laws of general relativity. So as you imagine, general relativity imposes some constraints. So not every possible singularity you can think of is doable. So you have to sort out singularity by singularity and check whether those constraints are satisfied or not. So for one with completely random deformations, he exhibited mathematically one type of singularity after another. He cataloged the types of singularity almost ad nauseam. Among them, none had completely random deformations. Therefore, he concluded, bringing his 40-minute lecture to a close, an imploding star with random perturbations cannot produce a singularity. The perturbations must save the star from destruction. As the applause ended, Charles Misner, one of Wheeler's most brilliant former students, leaped up and objected strenuously. So you can see Charles Misner. He is one of co-author of a very, very fat book on general relativity written by Misner, Thorne, and Wheeler. Many people know this book. Well, it's also a fantastic achievement, but it is only on general relativity. It's not on theoretical physics. Excitedly, and in rapid-fire English, Misner described the theorem that Penrose had proved a few months earlier. If Penrose's theorem was right, then Kalatnikov and Lifshitz were wrong. Okay, but who is Penrose? Who is Penrose? The Soviet delegation was confused and incensed. Misner's English was too fast to follow, and Penrose's theorem relied on topological arguments that were alien to relativity experts. The Soviets regarded it as suspect. By contrast, the Kalatnikov-Lifshitz analysis was based on tried and true methods. Penrose, they asserted, was probably most likely wrong. Okay, the epilogue of this episode took place 4 years later. Namely, one more type of singularity was found. Namely, 4 years later, in September 1969, Kip Thorne, I'm sorry for this spelling mistake here, I cannot change it now, it's PDF file. Kip Thorne, yeah, I keep confusing Kip Thorne with some other Kuro Thor, who has a very interesting hammer, and sometimes I make this. Kip Thorne was visiting Zeldovich in Moscow. Lifshitz came to him with a manuscript that he, Kalatnikov, and Vladimir Belinsky had written. Belinsky was a new character in this game. He was their PhD student. Now he is famous, as famous as the other two. They had found one more singularity permitted by the laws of general relativity. By the way, it is now called BKL singularity. It's very important in general relativity. Penrose was right. So here is Kip Thorne, who visited. Zeldovich. This is Zeldovich, and on a post stamp. So you can see that in Soviet Union, they had respect for scientists. And this is Vladimir Belinsky, probably a bit older than in this story. Probably this photo was taken later. Okay, so what was Penrose's result that surprised so much all the relativists? We have to understand this result. I have to go backward in time and outline briefly, just in 5 minutes, the history of black hole theory. Okay, so in order to introduce, to discover theoretically black holes, we needed Sir Isaac Newton to understand that there exists gravity, and gravitational force is a part of is subject to some laws. Next, using this Newton's theory of gravity, a British philosopher, John Michael, pointed out that light would not leave the surface of a very massive star if the gravitation were sufficiently large. Should such an object really exist in nature, its light could never reach us. And he even mentioned the existence of a critical distance from the center. This distance was independently, since Laplace doesn't quote Michael, it was calculated by Laplace. It was derived from the escape velocity from the escape velocity formula when we take light velocity for the velocity. Remarkably, we obtain exactly the Schwarzschild radius, even up to all the coefficients, which is a coincidence, because in fact black hole cannot be really described with all the properties by Newton's theory. So it is just a coincidence, however, very, very nice coincidence that this radius is the same. I know about this coincidence. Actually, every student in high school can check it himself, but I know about this from Professor Wróblewski. He was the first person to show me this when I attended his lectures as students, as probably many of us. Okay, but in order to have a real black holes, we need general relativity. So here comes Einstein and his equations. And now, just a year later, Karl Schwarzschild solves those equations for spherically symmetric case, and he finds his famous formula for spherically symmetric vacuum solution without cosmological constant to Einstein equations. However, that solution has a certain drawback, namely some coefficients which gives us, this is a lapse of time. Some coefficient vanishes for some finite value of r, exactly this value. And those days it was considered singularity, some drawback of theory, maybe theory doesn't work. However, Stanley Eddington and David Finkelstein, they introduced, probably independently, they introduced coordinates that extend space-time through this forbidden radius, and they show that in fact it's not a singularity, it's just a property of coordinates, just time coordinate is not anymore, does not work anymore. And now in 60s, very important for all this field and for all the relativity those days, work by Robinson and Troutman was published on new class of spacetimes, and they introduce a completely new way of new approach to general relativity by focusing on null geodesic flows. You will see today that those null geodesic flows are extensively used by everybody later. And as an example of some certain quest for, so their result, they assumed for simplicity that their solution is twist-free, whatever twisting means. Twisting means twisting of some null rays distinguished in this solution. So there was a quest for a solution that relaxes this assumption. And then who was the to win this quest, it was Roy Kerr. And he was not looking for black hole, he just was looking for an example of Robinson-Trautmann solutions that is generalized to twisting case. And what he found was a rotating black hole. Well, it seemed to be a very special case, maybe not strictly symmetric, but axisymmetric. Nonetheless, later, Ginzburg and his followers showed that actually Kerr's solution is a generic solution. It means black hole that is stationary cannot have local degrees, stationary degrees of freedom. It cannot be deformed. It has to be the Kerr black hole, and it can be described only by 2 degrees of freedom. So no Kerr means no local deformations of stationary black hole. The term black hole is due to John Archibald Wheeler. He used this, came up with this. Then Penrose's and singularity theorem comes, which is later followed he's joined by Hawking, and in 1970 together they publish a paper which contains the generalized version of original Penrose's result. Well, and still the black hole theory is developed by a group of gentlemen: Roger Penrose, Brandon Carter, Stephen Hawking, Werner Israel, David Robinson, Gary Bunting, and even there is a Polish name, Paweł Mazur. Well, unfortunately, he's not in Poland, but he comes from Krakow, from the Krakow School of General Relativity. So this is a story of black hole theory in one pill. Okay, but still there was this physical question. Can black holes exist in physical reality? Not only whether they can, but do they exist? Are they sufficiently likely in order to exist? Well, let us see what experts thought. So Albert Einstein in 1939 wrote a paper, and he says himself in the abstract, the essential, well, maybe not in the abstract, maybe it is copied from one of the pages. The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities don't exist in physical reality. Do not exist in physical reality. This is what he wrote this paper about. Okay, but that was 39. So let us look in the book of Steven Weinberg, written in 1974. This is book on gravitation and cosmology, principles and applications of the general theory of relativity. Very good textbook. There is a chapter on the Schwarzschild singularity. You have to remember that they used to call Schwarzschild singularity this point where of space-time where the horizon is. So it was not really what we call singularity. It was this horizon. And he says it should immediately be stressed that there is no Schwarzschild singularity in the gravitational field of any known object in the universe. Okay, so this was grain of salt. Maybe he doesn't really doubt in those results. However, he mentions this that we should remember. Okay, so as you can see, it was not absolutely obvious that black holes are really physical objects. Okay, but if black holes exist, then how they come to the existence? So the idea was that perhaps gravitational collapse produces a black hole. Yes, and this was first theoretical evidence, namely the Oppenheimer-Schneider model, who considered a contracting dust that was homogeneous and isotropic. In fact, it was a slice of closed Friedman universe. And they glued this dust with, so this is a ball made of this dust, with empty space. However, that space is endowed with gravitational field of spherically symmetric compact object. And they evolved this. Okay, and then they showed that the evolution of such data indeed produces horizon. So this matter, this dust collapses. It at some point, the radius becomes equal Schwarzschild radius. Then it continues shrinking. Horizon develops. Space-time is not anymore static inside the horizon. It is static outside. And at the end of the day, singularity forms inside. And actually, the final stage is that we have Schwarzschild metric with horizon, with the singularity inside, and the collapsing dust disappeared, except for it's leaking out of the singularity. So this model showed that there is a process that theoretical process that could produce a black hole. However, there was a big, people didn't trust this model because of very high symmetry of which was assumed here. Spherical symmetry of space-time and isotropic homogeneous dust. Well, so that model was generalized to non-isotropic dust, however, still homogeneous. For people who know cosmological models, this was some Bianchi type generalization. Well, Raichaduri and Komar, they generalized further. They actually gave up any symmetry completely, and they considered fluid instead of dust, which is generalization, however, irrotational. Okay, so what about a rotating perturbation? Perhaps they destroy the singularity. On the other hand, they were constructed models of converting which convert stars implosion into explosion. So imploding star was slightly deformed. Its atoms implode in slightly different points, swinging around each other and fly back out. So at the end, we have explosion. Well, and finally, there was this Kalatnikov-Lifshitz result that was published, it had been published in 61 or 62, so it was known as a serious evidence against those singularities.
You're at 10 minutes.
Okay, thank you. In the meantime, new geometric techniques were developed. So on one hand, we have Riemannian geometry that was developed very well by mathematicians, but for space-time, a lot of notions of Riemannian geometry changed their meaning. So there were similar methods, but in those methods, you have to switch sometimes signature, and what is minimalized is maximalized, and changes well, it changes a bit, that we have Lorentzian signature rather than Riemannian. So people responsible for those development was Trautmann, just himself, Robinson Trautmann, and later Bondi and Sachs, who introduced all program of studying null geodesic flows in space-time. So Penrose could be aware of all that. So that was his starting point. Okay, and now Penrose's revolution comes. This term, Penrose's revolution, comes from the book of Kip Thorne, so I'm not exaggerating, just for the sake of today's lecture. He had been already praised like this in 1990s. And this is Roger in 1980, so he's not that young anymore, but you can see he's a little similar to Colin Fells in Bridget Jones' movie. And this is Twister, or in other words, congruence, shear-free congruence introduced by Robinson and Trautmann, which is actually also Penrose's Twister. So that Penrose can draw by hand. This is hand drawn by Roger, so he can demonstrate drawing of such complicated figure whenever you ask him. Okay, and now the first paper by Penrose comes, Gravitational Collapse and Space-Time Singularities. This is this key paper. And let me explain to you what is the fundamental question and notion which he solves in this paper. Namely, can the future have a compact closed boundary? Okay, if I ask a philosopher or a poet, then probably he or she could have a lot of thoughts. If we are more mathematically oriented, we have to see what we are talking about. So let us consider a point in space-time. Then the future of point is interior of this cone, and the cone itself is the boundary. So can this boundary be closed and compact? No way, it can. Well, what about if we take extended object? Well, again, future is contained in some sort of cone, and then the boundary are those null geodesic curves. Certainly, they don't set anything that would be non-compact. So certainly it's impossible. So that was Penrose's idea, that such things cannot happen. But why did he bring up this idea? Okay. So he considered trapped surface, notion of trapped surface. In order to understand trapped surface, let us first think of a regular non-trapped surface. So for a non-trapped sphere, so this black ring is a sphere. There are now light rays going in direction, and they form converging flow. On the other hand, there are light rays going out, and they set diverging flow. Okay, so everything is as it should be. The one going in converge, going out diverge, nothing special. Okay, now Penrose is considered Penrose's trapped surface. So in case of Penrose's trapped surface, there are again those light rays going in, and they're again converging. There are again those null light rays going out, but already you can see from this picture that something is fishy about them. Okay, and in fact they are converging too. So his definition was, if there exists such sphere that has this property or such closed surface, then it is a trapped surface. Okay, and why did he brought up this issue? Namely, in Oppenheimer-Schneider spacetime, there really are trapped surfaces. So here was Penrose's idea. Oppenheimer-Schneider spacetime is spherically symmetric, very, very special case. It's not clear whether deformed, it still has those properties. However, the notion of a trapped surface is stable with respect to deformation. So if we understand trapped surfaces, then we also understand perturbed, even finitely perturbed Oppenheimer-Schneider spacetime. Okay, and then Penrose studied the properties of trapped surfaces. In general case, he considered a three-dimensional surface. This is exactly this boundary of the future of this trapped surface. And then by using fantastic geometry and fantastic mathematics, many lemmas, many steps, but all of them beautiful and very clear, he proved that this surface is achronal. It means every 2 points cannot be connected by, any 2 points can be connected by time-like curve, compact and closed. So it has this property we're just talking about, namely that future of the trapped surface is compact, the boundary of this future is compact and closed. And now Penrose proves it cannot happen. So this is the cartoon version of this proof. I suppressed some dimensions. So this is this three-dimensional boundary of future of trapped surface. This is the space of initial data, the Cauchy surface. And this is a family of time-like observers. This family defines a one-to-one homeomorphism between this three-dimensional closed surface and a ball in R3 or some other non-compact three-dimensional manifold. And that cannot happen. And that was Penrose's point. So in this way, he showed, proved that a perturbed, but finitely perturbed Oppenheimer-Schneider model will also develop singularities. And this is original drawing by Penrose. So you can appreciate probably my drawings when you see this. So this result attracted a lot of interest. Penrose was joined by Hawking, and then Hawking immediately dragged the research toward cosmology. So Hawking was working on application of this idea in cosmology, Penrose on his own, but then at the end, they noticed that if they combine their results, they actually get a new result, real synergy. And then they published in 1970 a paper on singularities of both gravitational collapse and cosmology. And in this paper, they are able to actually relax many assumptions. And the main result, this most general version they obtain is the following. So space-time has singularity, which means cannot satisfy causal geodesic completeness, if, together with Einstein equations, the following conditions are satisfied. Those conditions, they don't like each other. So M contains time-like curve, no closed time-like curves. Well, this is a reasonable assumption. Certain energy condition is satisfied. Energy is positive. This is basically this condition. Certain generality condition is satisfied, which means certain certain component of Riemann tensor does not vanish. And then M contains either a trap surface, this was the case discussed for black hole, either a point P such that convergence of all the null geodesics going in the past changes the sign somewhere later. So if there is such point, then it's also not good, and there is the singularity is formed. Finally, the last case is a compact space like hypersurface, which is, for example, the case of closed universe. So here you have application to cosmology. So this was the final result. Now, how much time do I have? Probably 0.
You are right. Yeah.
Okay, so let me skip. There is some beautiful technical formulation, but then I can skip it. And now, conclusions. Okay, so the conclusion on singularities is that singularities are realistic consequences of gravitational collapse. And it also applies not only to stars and galaxies, but also to universes. The singularities amount to incompleteness of some geodesic curves. However, not much is known about the nature of those singularities. So whether what really explodes is not known from those papers. Can we see singularities? This is another issue. And actually, in order to prove existence of black holes, you want to show that we cannot see singularities because they are hidden behind horizons. And here we have only Penrose's cosmic censorship conjecture. Many people worked on this. Is his conjecture true? Well, yes. If the Penrose inequality is satisfied, then the black hole horizon forms. But is the Penrose inequality true? Many mathematical relativists works on this. Penrose also is author of other results on black holes, which are not in the topic of this lecture, so I can skip them. This is illustration for one of the results, which is instability of the inner horizon in the Kerr black hole with respect to falling matter. So we can also skip. And Penrose is also an author of many other famous results. And the most famous are existence of quasi-crystals, which follows from aperiodic timings he introduced. The twistor theory, and this is a twistor. Spin networks, which we use in quantum gravity. And impossible objects that inspired painters, one of those objects. So, okay, this is it. In conclusion, Penrose achieved so much. He came up with so many ideas and solutions that singularity theorems is only part of them, and I'm really happy that he received that Nobel Prize. Thank you.
Thank you very much. It was a very nice talk, very beautiful, illustrated. If we have another talk, but let's spend 5 minutes if there are any questions direct to Professor Lewandowski at this moment of time. So if
Can I ask a question?
yes, please.
So very simple question. So in the formation of the black hole, from the point of view of external observer, the time it takes to form a black hole is infinite. Yes, I guess.
Yes, that's true.
So I wonder what's then your opinion on the existence of black holes, which we will listen in the next part of the talk. If the formation takes infinity, that means we cannot observe it, like the whole evolution, explosion of a star and formation of a black hole. So we can only see the black holes that already were existing before we started observing, or what? What kind of black holes we can observe?
Not really. I think what we can see is, yeah, there could be pre-existing black holes, but most likely there are only those black holes which are formed by collapse. But we can just see if this collapse is sufficiently develops, then well, we can see by looking at black hole that at a star that this is at final stage of collapse. So we can just we can see many effects of black hole even before it becomes a black hole.
So actually, this question brings us to another to the second part of this colloquium. So let's thank Professor Lewandowski again for his nice talk, and then please stop sharing the screen, and I will ask now Dr. Wyrzykowski to share his screen.
All right. Hello, everyone. I hope you can see. Let me just begin.
Yes, we see it, but not in full screen mode. So if you can.
Is this now better?
Yes.
Okay.
Yes.
I hope you can see it. Okay.
Okay. Thank you. So please, 30 minutes.
Thank you very much for the invitation first. It's an honor for this opportunity to present the Nobel Prize in Physics, which is so closely related to astronomy and also to my personal research interests. And actually, I've given a subtitle, pre-title of this sub-lecture, How to Measure Black Hole Mass and Receive the Nobel Prize in Physics, because this is, in my view, that's the prize. This is what the prize was for the second half, at least. So here you see pictures of all three Nobel Prize receivers. I'm going to concentrate on the second part, which was received by Richard Genzel and Andrea Goetz. So I will begin actually with after this beautiful introduction by Professor Lewandowski, we'll begin with this debatable birth of a black hole. This is, of course, an animation showing a supernova explosion. This is how our understanding has developed since these discussions in the 1960s, whether we can actually form a black hole from stars or not. This is what we observe these days, and we see supernovae exploding in other galaxies. We see tens of supernovae exploding. So we see black holes forming just in front of our eyes. We just need a massive enough star, and the mass is about 20 solar masses or more for such star to collapse and form a black hole. Of course, I have to mention gravitational waves and the observations of merging of compact objects. This is another proof of black holes existing. At least we see some objects collapsing and they form an even more massive object, and the masses are again of order of tens of solar masses here. And I'll just remind you that this was a Nobel Prize in 2017 for the discovery of gravitational waves, and actually for the discovery of black holes of this form. But the Nobel Prize we're going to talk about was related to our galaxy, the Milky Way. Actually, if you look behind me, I have a Milky Way map just behind me, and just behind my head, there is the center of the galaxy, where we understand the black hole and the supermassive black hole resides. This is on my slide. This is an artistic impression how we imagine our galaxy to look like if we were able to travel thousands of light years above the galactic plane, and the location of our solar system is marked with the red dot here. So let me start with the history, a little bit of history of Milky Way black hole. So in 1969, Donald Lindell proposed that all galaxies have supermassive black holes. I will use this acronym SMBH for them further on. In 1971, Lindell and Martin Rees, they hypothesized that Milky Way can actually have its own supermassive black hole. In 1974, Balik and Brown, they discovered a radio source. They called it Sagittarius A star or asterisk. And I found that they called it A asterisk because it was an exciting source. And also it was a result of excited states of atoms releasing cyclotron radiation. In 1992, first high-resolution image of the stars near Sagittarius A star were observed, and it was done with a 4-meter telescope at Eso in Chile. I will talk more about Eso in a moment because it played a significant role in this discovery. I'll just say that the American partners, they used Keck Telescope from Hawaii, and they got their first image of the same location in 1995. This is when the competition, kind of the healthy competition, began between European Southern Observatory and the Americans. So this in next years, between 1995 and 97, Eckhart and Genzel from Max Planck Institute for Extraterrestrial Physics, they published series of papers showing showing motion of stars within very small angular distance from Sagittarius A star. Andrea Goetz from University of California, Los Angeles, published a similar paper in 1998. So the conclusions here were that there might be a massive and very dense object related with Sagittarius A star. There is a Polish twist to this story as well. I found in 1998, Michał Jaroszyński from our observatory and Bogdan Paczyński from Princeton, they suggested that long-term monitoring of stars next to the black hole can help derive black hole mass and also observe relativistic effects. So these are they published a set of papers related to this. And then in 2000, there was a paper led by Guess, 2002, a paper by Eckhart, 2002, another paper by Genzel Group. So they published the results showing the motion of one of the stars. They called the star S2. They published the motion of the star near Sagittarius A star, monitored over about 10 years. And in 2008, Guess published Keck results from showing astrometric measurements of the positional measurements of this star and radial velocity, covering 12 years of observations. And she estimated the enclosed mass of 4.1 times 10 to the 6 solar masses. In 2009, Gillesen, that's a collaborator of Genzel from Max Planck, they refined astrometry. They published the refined astrometry of 16 years of Eso data with superb precision of 0.3 milliarcseconds. Since 2016, Eso has installed Gravity Interferometric Instrument. That was actually a dedicated instrument for Milky Way supermassive black hole observations. And this was part of the Genzel and Gillesen research. So if we look into our galaxy again, this is where the very center of the Milky Way is. This is in the Sagittarius constellation. You see that this box is showing the very center of the Milky Way. So this is where we see stars, but these dark patches, these are patches of dust. In the visual wavelengths, they cannot pass through. They are just absorbed by the dust. And that's why we don't see the very center of the Milky Way. That's why these observations, they have to be performed in infrared. It doesn't have to be very far infrared. It's enough to go to microns. And here at the top, you see the image taken by Vista telescope in near infrared. You see, if you compare it to the optical image, there is way more stars, and actually the very galactic center is observable now. So we can see the stars. So the first condition, that if we want to monitor what's going on in the very center of the galaxy, we need to observe in infrared. Another condition is high angular resolution. We need to look into the very heart of the galaxy and resolve stars, which are very, very close to each other. This is just an image of this, and you see 1 arcsecond in 1 arcsecond, there's plenty of stars. We want to monitor all those stars with high precision. So this is, I just described the technicalities, how it was done, but I would like to emphasize that from the very beginning, both Nobel Prize receivers, Genzel and Guess, they were very active in developing techniques in order to achieve what they eventually have achieved. So the observations at very high angular resolution in order to monitor, long-term monitor the stars near the galactic center. So this is ESO. ESO, European Southern Observatory. Poland is proudly a member of this organization. This is an international organization. Poland has joined in 2005. So we have now access to those telescopes. And the telescopes you see here are 4 major horsepowers of this observatory, although ESO has many other smaller units as well. So this is important that ESO is located in Chile. From Chile, you can actually see the Sagittarius constellation throughout a significant part of the year. So Chile is very well located, and ESO observatory is well located if you want to monitor the Sagittarius constellation. Also, Chile is, of course, perfect for astronomy because of very dry air, and there is very little turbulence due to air. The observatory itself is located at about 4,000 meters. That also helps to minimize the atmospheric turbulences. But still, there are some turbulences even in Chile at high altitude. So people have developed adaptive optics. This is just to show you an example how it works. This is a technique which requires monitoring of the turbulences. You can have high altitude layer turbulences, you can have ground layer turbulences, and you need to correct your observations to those. So you measure a star, a reference star. This could be a star next to your target, which is bright enough. You monitor the behavior of such star, and you correct the mirror in order to counteract to the turbulences. So ESO has been equipped with those, the adaptive optics instruments. Therefore, you can beat the atmosphere, and you can increase the resolution of the imaging by a factor of 10, as you see an image, distorted image of a star here, and corrected image with full width half maximum, which is 10 times better than here. Especially the addition of laser guide star system in ESO improved this much more, because now you don't need a natural star to guide your system. You just create your own star wherever you need it. So you see on the image here, these are the sodium lasers which are shot into the sky next to the observed target, and then the reference stars are produced on the image, and therefore you can correct for the wavefront depending on the turbulences of the air. And then, of course, there is Eso Gravity Instrument. This is a really high-tech instrument developed by Max Planck in Germany, in Munich. So this is a 4-channel K-band, so microns, interferometric high-resolution imager. The difference here of this instrument is that it combines the beams of light from multiple telescopes. And gravity is actually installed in this observatory in Chile. And it can use input from any of the telescopes. So you can use the major units, which are 8-meter telescopes. You can combine 4 of them and you gain a lot of signal, or you can use smaller telescopes called auxiliary telescopes marked here. You can then increase the resolution because the baseline is much broader for these ATs. But you lose sensitivity in terms of light. But the resolution here, which is achievable by gravity, is of order of milliarc seconds. So this is about 2 milliarc seconds for ATs and for UTs. So this is state-of-the-art instrument, which was, I would like to emphasize, this was built, this instrument was dedicated for the Milky Way supermassive black hole observations. Now I will tell you about the American part of this. So the Keck telescopes are 10-meter. There are 2 10-meter telescopes in Hawaii. You can see the domes of these telescopes here. So the Hawaii is the another place which is great for astronomy because of altitude and very low humidity of the air and low turbulences. However, as you can already imagine, observations of the Sagittarius constellation are a little bit more difficult from Hawaii. On this very image, actually, you see the laser guiding systems, which they also have, shooting into the very galactic center. And the galactic center is at somewhat lower altitude. So there is less time from Hawaii you can observe the galactic center than it is in Chile. Nevertheless, it's still doable, and they did a great job observing from Hawaii as well. Keck has also the laser guiding system for AO, and this is an example how the image improves if you turn it on and off. They also used speckle imaging, which is sometimes called speckle holography. You just collect your images with the frequency which is higher than the frequency of the turbulences of the atmosphere, and then you can select better quality images. So you can improve the precision of your imaging and resolution by many factors. So these are the main techniques which were used by Andrea Goetz at Keck. So what they actually did see, so this is an animation, I hope it plays, yes, this is an animation of all these stars. If you go through all this dust and you see stars, you can resolve the stars, you can trace how they move. So these are the positions of stars, how they change over time. And you see this is a period of dozens of years. This is still very slow, very fast. I mean, even though it's slow, but this is the time required for observations. You still require decades. However, this is for astronomy. This is a very fast event. Normally, we deal with events which have timescales longer than a human lifespan. So this was the observations they managed to collect. This another image is just a nice visualization from Keck. So there's many stars. The SO2, or sometimes they call it S2, was the one which reached the closest to the Sagittarius A star. But people were able to trace the positions of multiple stars. And this is kind of the final result, what you can get. This ellipse here, shown here, this is the positional offset of the star with respect to Sagittarius A star, all collected over almost 18 years here, or 16 years. So this is the full orbital period of the star around the black hole. The pericenter is marked here. It was reached in 2018 in May. But all these data points, they were collected by both groups, Genzel and Guess. And this, I will actually embed the Nobel Prize here. This is the Nobel Prize image. This is how they managed to collectively managed to measure the mass of this object. So let me emphasize the technical difficulty reached here, going through all this dust in infrared, beating the resolution to the finest levels. Okay, what they were also able to observe, and it was published in 2018, was the gravitational redshift. So the star S2 near its pericenter became redder, which was in perfect agreement with gravitational, with general relativity theory. When you have the light rays passing next to a black hole slowing down. So this is actually pretty cool that you see the effect of black holes mass on light rays so directly. Another interesting thing which happened in the meantime, kind of, was the observations of gas cloud, which was called G2. This was the cloud of some gas cloud. People debate what is the origin of this gas cloud. Some people suspect this is the atmosphere of a star which was there at some point. So people were able to observe the disruption of this gas cloud next to the black hole. On this animation, you also see the traces of the orbits of other stars next to the black hole. Interestingly, we see such disruptions, and I will do some advertising of our recent detection of a black hole in some other galaxy that revealed its black hole thanks to a star which was killed by spaghettification. That's a nice name. This is what happens to a star when it gets too close to a black hole, and then the tidal forces essentially disrupt the star. Half of the matter, more or less half of the matter, is accreted onto the black hole. You see the accretion here on this animation. Accretion results in formation of the jet. There's the accretion disk formed for a short period of time. And then part of the star survives. But we see the emission of light temporarily. We detect it as a flare lasting maybe few months, maybe few years. It depends on the black hole mass. But generally, these events are being seen in other galaxies, as we kind of expect, because we now know that other galaxies, they also have black holes. So detection of tidal disruption events like this one is one of the ways of proving black holes exist in other galaxies. Okay, where's my next slide? So yes, so people measured masses of black holes of other galaxies, and we know that these black holes exist in other galaxies. These masses of black holes, they form this relation m sigma relation, where sigma is the dispersion of the velocity of stars or masers or gas next close to the black hole. So these are methods of measuring the masses of other black holes. What is interesting, what we see here, I marked the Milky Way mass here on this plot. The Milky Way is a lake-type galaxy, which means, as usually in astronomy, it's the other way around. It's fairly young galaxy. It's not old galaxy. So the older the galaxy, the more massive black hole it has. Even more, the most massive ones, like those here, 10 to the 10th solar masses, they tend to reside in bright cluster galaxies, like this one here. An example of such a black hole is M87, which became famous recently. This is the image of the galaxy as a whole, and this is the black hole image taken by the Event Horizon telescope.
10 minutes.
Yes, of course. Thank you. Another types of black holes we know of are quasars. And actually, I've seen on some of Professor Lewandowski's slides that Penrose was aware of existence of quasars, and that's why they started to think about black holes' existence. It took a while for people to realize what quasars are. Now we know there's this unified model of a galactic nucleus, where there's a black hole, there is a accretion disk, there is fast-moving clouds, and there is this dust ring, and so on. So this unified model kind of works. There are some people who try to undermine it, but anyway, we can see those quasars very far in the universe because they're extremely luminous. The difference between a quasar and our own Milky Way black hole is that quasars consume matter all the time. They are still being fed by the accretion disk and the matter flowing onto the black hole. Actually, here you see also an image of this torus taken by the Hubble Space Telescope. This is probably the only formula I have on my slides. This is how people normally measure masses of quasars. They take a spectrum and then they can measure the Doppler broadening of the material which is floating around the black hole, the broadline region, so-called. You can measure the dispersion from this Doppler broadening here, and you can derive the mass. And actually, my colleague from the University Observatory, Szymon Kozłowski, recently he has measured masses of black holes in about 300,000 quasars. And these masses span from 10 to the 7th to 10 to the 10th solar masses. So we know of many black holes existing in quasars. But there is one problem, kind of, where those quasars came from. And this is a recent discovery of a quasar with mass of about 10 to the 9th solar mass. But the problem with such quasar is that this one is very far away. It's at the universe of at the age of about 800 million years. This is the discovery image. So if at such an early age of a quasar, you already have 10 to the 9 solar masses. So what these people did, they extrapolated the growth of such a black hole far into the redshift, into the beginnings of the universe, and they found out that even at the very maximum growth speed, you still need 10 to the 3rd solar mass, black hole mass at the very beginning of this quasar. So you need those, they call them seeds of those supermassive black holes. This is another graph showing the visualization of this. So very early in the universe, you need to come up, you need to have some seeds in order to form the black holes we observe in more modern universe. So they grow via accretion and mergers, these quasars, these black holes. However, you need some kind of smaller seeds, and these low mass black holes are called intermediate mass black holes, and they can be formed by very massive stars very early on. They can be formed by some clusters in protogalaxies, some small protogalaxies, and then direct collapse of those. This is not well understood yet, but the conclusion from this graph is that we should see some leftover IMBHs in the current universe, which were formed very early on. Some of them were the seeds for the supermassive black holes, and some of them remained. And I will emphasize here that there is an alternative theory to this, published recently by Professor Meissner and Nikolai. This is a very interesting topic. It is this kind of the consequence of these discoveries of supermassive black holes in the galaxies, in the centers of galaxies. Yes, there are some hints of intermediate mass black holes seen accreting. So I just emphasize, show some examples here. We see IMBHs in gravitational waves. This is an interesting connection to those low mass, to the low mass end. We've seen a black hole of 142 solar mass being formed in a merger. Some people like Chris Belczynski, they claim you can form such black holes just from regular stellar evolution. You see the evolution here. You need low metallicity, very massive stars at the very beginning, but we can form these IMBHs. So just to finalize with the future, what can happen next, what is happening now after all these discoveries, there is a plan for Eso Gravity Plus, which will beat the gravity 10 times better in angular resolution and in sensitivity as well. It can detect IMBH next to Sagittarius A star. This is a very interesting avenue. Of course, it can do many other things like finding black holes in gravitational microlensing events as well. Another step is the ESO Extreme Large Telescope. It's going to be 4-meter telescope, which will start operation in 2030 in ESO. And one of its instruments, a multi-AO imaging camera for deep observations, will have superb astrometry, all the laser guiding systems, and so on. So I will stop here, and thank you for your attention, and I'll take questions if there are any.
Thank you very much. So we have time for questions.
I have one. Krzysztof Meissner is here.
Yes, please.
So, what is the oldest or the closest to the origin of or let's light scattering surface black hole that one can possibly see with these techniques?
Well, I think the closest one, the oldest, is probably the one I've showed here at redshift about 8. Yes. Maybe since there were some discoveries further on, but this at this moment, this is the furthest we can see.
But is there any limit, observational or whatever, that you cannot go further on to, I don't know, 400 million or 100 million or whatever?
I think it's a matter of sensitivity. You just need to go very faint, and you need to observe in very far infrared, because these quasars they are very high redshift, right? So I'm sure with ESO ELT, with this telescope we see here, we will be able to detect those very faint ones and the very, very distant ones.
Okay. But when, some approximately?
I think in the next decade or so.
Okay. Thank you very much.
Other questions or comments, remarks?
May I?
Yes.
Marek Biesiada is speaking.
Yes.
And
please.
I have a question to Professor Lewandowski, and namely that now that we know that the universe is accelerating our expansion, it is sort of dominating by the, say, cosmological constant on something mysterious we call dark energy. And my question is that the Penrose results are global, and are they affected by this fact? For example, that the asymptotic is no longer Minkowskian but the de Sitter, or that the energy conditions break down, if this is the truth about the nature.
Yes, this is a very good question. So let me start with what is really, where really there is some measurable effect of this cosmological constant. So technically in the proofs of those theorems, Penrose either considers null geodesics, as in this first theorem, which I discuss even in some detail, or he also considers time-like geodesics, as in his works in Hawking. So whenever we consider time-like geodesics, then we have influence of the cosmological constant in all the equations. And then, unfortunately, the positive sign of cosmological constant goes against the what we want to, all the inequalities. On the other hand, the good news is that for this part where we consider only null geodesics, like this first theorem on the trapped surfaces, then this cosmological constant, since it produces in Einstein equations term proportional to g mu nu, and it is contracted with null vector, so anyway it is zero. Those theorems, they are also true for non. So this is a sort of local result because this theorem on well, in a sense it is a global theorem, but it's a quasi-global theorem. So we don't really have to know all the structure of space-time, whether space-time is if it has topology of cosmological model or asymptotically flat or asymptotically de Sitter, because we just talk about formation of black hole singularity. Yes, so as far as formation of black hole singularity is concerned, those main theorems are true, as long as they don't use this cosmological additional support, which comes from Hawking. So this original paper of 1965 is true. Those papers proof which were written later, well, they may also be true, because if you relax some assumption, it doesn't mean that there is immediately contrary example, but probably one would have to, well, since this cosmological constant is very tiny, so maybe it doesn't change those inequalities so much. Now, the second part of the question is about the global structure of space-time. So indeed, for black hole looks differently from the point of view of asymptotically flat space-time and from the point of asymptotically de Sitter, but somehow the power of this definition of Penrose, according to which event horizon is a boundary of the past of the null infinity. So actually this definition is valid for arbitrary kind of asymptotics. So as long as we have a conformal completion of space-time and there is well-defined asymptotic boundary, this conformal boundary, the black hole is well defined. So this part is valid also for cosmological constants. So you can see conformal diagrams for Kotler metric, which is Schwarzschild, sometimes called Schwarzschild de Sitter, or for Kerr de Sitter, and they are, you can see the black hole on those diagrams as well as on the usual diagrams for asymptotically flat case. So thank you for the question.
Thank you.
I can see a question in chat, which was asked by Mr. Konrad Buda, a student of Dr. Machalski. What will be the future of the universe? Jurek.
Wow. Well, it's a very serious question.
Right.
Well, I think it's just expanding, so maybe it will get more and more empty and then boring, except for some regions where matter will concentrate, and then they will be lively.
Okay.
Except when Penrose is right about CCC. Then we'll
well, this goes even behind the future, because then we have after we are done with the infinite expansion, then we will have another aeon and another aeon and another aeon. So yeah, that's true. That is a good point. Roger also
I have a question.
predicted.
That's it, Pawełczyk. Yes?
Yes, to Dr. Wyrzykowski, Professor Wyrzykowski. Well, I want to ask about the other end of the story, the lightest black holes. What can we say about these guys?
Yeah, this is an interesting avenue of research, actually. So far, we see the lightest black holes in X-ray binaries, so that where there's a star and the black hole, a compact object, is consuming the star. We see their masses are about 5 solar masses. And then there is this gap, and then the next compact objects we see are neutron stars with the maximum mass of about 2.3, more or less, solar masses. So now the story goes that in gravitational waves, people started to see objects which are compact and they fall within the mass gap. So we have no idea whether these are overmassive neutron stars or they're the lightest black holes. We can't tell from black holes alone. With our studies with microlensing, we also see some candidates for very low mass compact objects, yet we don't know what they are. We cannot distinguish neutron stars from black holes. I hope, well, it answers your question.
Okay, thank you
So I
very much.
wanted, may I just add something? Yes, Dorota Rośnińska z tej strony.
Yes.
Just I wanted to, I'm very happy that Łukasz mentioned these results of binary black holes, which we observe using LIGO and Virgo gravitational wave detectors, because we really have very, very interesting binary system in which containing, let's say, mystery object, which is 2.6 solar masses. And we don't know if there is really the lightest black hole or the most massive neutron star. And unfortunately, it was at such kind of frequency that we were not able to see. I mean, that there was something like that, that the difference between these masses, the black hole and this lighter object was quite huge. So probably this object was eaten, you know, just as a wall, not disrupted by tidal forces. So this is why we don't know what was really that. But in close future, we supposed to observe plenty of such kind of objects. And also the second comment maybe to the first question, that in gravitational waves with the future Einstein telescope gravitational wave observatory, the third generation observatory, we would be able to see the mergers of all intermediate black holes in the all universe. So really, really starting from the very beginning of the universe, you would be able to observe this.
I can see another question in the chat from Jan Kotlarz. Would observations from balloons be useful in that respect?
Okay, I can
From
try
high
to answer this one. I can say that, you know, from balloons, if you go above 50 kilometers, of course, you beat the atmosphere, you don't have the turbulence anymore. But on the other hand, you have the problem of stabilization. So if you can launch a gravity instrument on a balloon, that would be extremely useful, but I think it's not yet possible.
Okay. There was a question about this light or small black holes, but what about mini black holes? That, you know, some 20 years ago, there was a big discussion about possibility of creating them in PP collisions, proton-proton collisions, that would eat up the universe. Is this topic still being discussed or forgotten? I haven't heard anything recently.
I think this is beyond astronomy, so we don't reach to such a low masses.
But maybe Jurek can say something about.
So as far as I remember the values of charge, then I think that such a black hole which is formed by a single proton or electron, it wouldn't be a black hole. It would be a naked singularity without horizon. So it would be a singular object, but without just. There is some limit on the charge of black hole, and in that case, this charge of elementary particles is far above this limit.
Okay.
Hello, I have a question.
Who is speaking?
It's Anjan from FUW. I'm a student of Masters in FUW.
Please.
So I have my question to Professor Lewandowski. So my question, I think, will get drifted from the topic, but actually I'm curious about that. So we heard about the gravitational waves from Keck Telescopes discovery in 2017, and after the Nobel Prize was awarded. So my question is like, I actually read about the inflation theory during the starting of the universe after the Big Bang. So my question is what would be the behavior of the gravitational waves during the time of the inflation? Like I saw some papers on internet, but I couldn't understand because I haven't read much of that. So like a generic question, like what can we study from them?
I don't know. I'm not an expert on gravitational waves in the context, especially in the context of inflation. So I don't know.
Okay, sir. Thank you.
Okay, so I think that it's time to close our meeting. We had quite a few questions, but time is running out. So let me thank Professor Lewandowski and Dr. Wyrzykowski for very nice lectures. And just in few days, there should be a recording available on the webpage of the our colloquium. So then you may have a possibility to see it again or hear it again and go through transparencies. So thanks a lot. And I close the meeting.
Thanks a lot.